All right, so for problem 13, I've chose something that's pretty similar, which was problem 14 in the textbook. Okay, so for this, we have to show that if A and B are sets with the same cardinality, then we have to show that this is true. Okay, so to prove this, we're going to utilize the definitions in the book. So the first definition that I'm going to use was, I think it's there exists a one-to-one correspondence from A to B if and only if the cardinality of A is equal to the cardinality of B. Okay, so that's the first definition. And the second definition that I'm also going to use to prove this is also in the textbook. There exists one-to-one function from A to B if and only if the cardinality A is greater than the cardinality of B. Okay, so to prove this, first I'm going to take a look at this part. So from here, given, this suggests that this is true. The cardinality of A equals to cardinality of B. So from here, we can go back to the first definition. We know that there is a one-to-one correspondence of F from A to B. So using from the direct definition of one, the first one, this gets us to the fact that by the definition of one-to-one correspondence, this also means that their F is also one-to-one function from A to B. Okay, so one-to-one is satisfied just using the definition of the first one. All right, so I think we were able to prove this. Now let's go to the second part. From the second of the cardinality of B is less than or equal to A. Okay, so from this, I'm going to try to show that cardinality of B equals to the cardinality of A, because that's what it's suggesting. And it's pretty much the same thing. This is by the definition of 2. We're going to define this is a function, which also gets to the definition of one-to-one correspondence. So give it a try and take a few moments to let this kind of sink in. You're using the definitions to show or prove these cardinalities, and by doing showing the first part and the second part, just using the two definitions, we can come to the conclusion that what they're trying to show is satisfied. All right, so the last problem I would like to go over 16, which hopefully this will show how to prove problem 15. So for this problem, actually, I'm going to use problem 15. I'm going to assume that you were able to prove it and use that to prove this problem 16. Okay, so let's suppose we have this relationship where A is countable. Okay. Then, because of 15, which states that if set A is countable if and only if there exists a one-to-one function, and that one-to-one function, we're just going to write it here. It's going to be from A to the natural number n. So because of number 15, due to 15, we can say that there exists a one-to-one function, and let's say that F and A will be mapped to n, and this would be a subset of just a natural number. You can say this, or we can also say that there exists a bijection. Okay, so, or there exists a bijection of the mapping from A to the natural number A, n. So we can do by the first way or the second. Either way, we have the one-to-one relationship from the mapping of A to the natural numbers. So because the natural numbers are countable, we have satisfied and shown that a subset of a countable set is also countable. These proofs can be tricky, and you might not be able to see it immediately. I think I'm gonna, if I were to give these proof-based questions on the exams, I will provide you with more practice problems and the solutions. But it's a good practice to be thinking in discrete math, to think about how to prove using either finite or infinite numbers.